All right, with that, we're going to start our first topic, which is runtime analysis. I hope you have seen these words before. Have you? Runtime analysis. You've done runtime analysis in your data structures, right? Okay, raise hand if you have. All right, that's more like it. Okay, cool. We're going to start with first example. It's a problem which says that I'm going to give you a list of n distinct numbers. I'm going to ask you to find the largest one of them. And you're supposed to write an algorithm for that. All right, so what's the time complexity of the algorithm to solve this problem? Yes? Green jacket, yes? O of n, okay, big O of n. That's correct, thanks. So I had this question. It's not going to work. So this is the algorithm that you probably had in mind, and probably everyone else does, which is that you kind of start with the first number in the list, and you compare it. You store it in a temporary variable, and then you run a loop to compare that temporary variable's value with everything else in the list, and update it the moment you see something which is larger than what you had in the temporary variable. And that's going to give you the largest. So you can write it in Python. You can write it in C++. I actually wrote it in a bunch of languages. And the problem I see there is, okay, let's just, you can still see my screen, right? Okay. People, no talking. Hurry up. Okay, so I guess this is the one. You can see my pointer, right? Okay. So I wrote the same problem, same algorithm in C++. It does what we had on the slides, and in assembly language, in Go, right, so this is what I'm doing, right? JavaScript, same algorithm, okay? And then then what do? I try to run it using this code. Max / okay, somewhat visible, I don't know. This usually takes 10 seconds on my, oh, okay, it's there. Cool. So what I wanted you guys to see is this table. Can I go? All right, so the point I'm trying to make here is that look at the third column, which is the mean amount of time it takes to run this. Guess? Okay. We try to. Better? Are we good? Okay. So the point I'm trying to make here is that if you look at the third column, which is the mean amount of time it takes to run it on a bunch of these trials, which just do this, which find the maximum of a list of, I think, about 10 million numbers. Just give me a second, okay? Is it about, can you see this? Oh, you cannot see this, okay. Can you see over there as well? No? How about now? How about now? Okay. Where's Amna? Amna, can you see this? Okay. And now it's just jumbled. No, it's all right. It's okay. So this is the column I want you to look at. Okay? The mean. Can you see this now? Okay, thanks. Everyone? Can we see this? People, especially the people in the last row, second last row. Okay. So the point I'm trying to make here is that it takes drastically different run times if you look at this clock cycle of your machine, depending on which programming language you took to implement the same algorithm. Okay? It's the same algorithm, right? It's the same algorithm where you have a temporary variable, you put something in here, and then you run one loop. Okay? For example, in Go, it's going to take about 58 seconds or milliseconds. Rust, it's 27, compared to C++, where it's taking. I'm actually a bit surprised that C++ is slower. All right? Right? So that's the point. That programming language is very. If you look at the clock time of your machine to judge how long it took to run an algorithm, that's not a very good judge, because it depends which programming language you use to encode your problem. Okay? Not just that, but also the hardware. If you run it on, for example, M2 or M4, it's going to be drastically different. All right, now I am in here, view, what? Almost there. What do I do now? I don't want that. Oh, it. Okay. Cool. Over here. Yeah. Okay. We're a bit slow. All right. So it depends a lot on programming language, hardware, and current system load, and they're going to decide how long it's going to take. Okay. The idea of an algorithm is that you want to skip all that detail. Okay. Instead of doing that, you want to count the number of primitive operations that are in that algorithm. Okay. So, or instructions here. Okay. So what do I mean by primitive operations? Primitive operation could mean different things depending on different problems. For example, if we are in the domain of finding maximum, can I turn the lights back on? Okay. Then for finding maximum, comparison seems like the right primitive operation. At times when you are doing sorting, you will count the number of comparisons. At times, comparisons is not going to be the right primitive operation for sorting. And you will be counting, for example, the number of movements from one data space to another memory space. Right. Okay, so for this one, the algorithm is what you have already in mind, which is that you keep the first variable in a temporary, keep the first number of the list in a temporary variable, and then compare it with everything else, okay? And the number of comparisons for this one is n-1. And the idea is this is independent of the hardware and the programming language, okay? Algorithms are abstract implementation, the abstract implementation details. Efficiency is, or time runtime is measured by counting the primitive steps. This allows us to compare algorithms by abstracting out the hardware details. All right. That I'm gonna skip. I assume that it's all right. So we avoid using the wall clock time because it depends on the language and hardware in the system load. Okay. Okay. Next, we are going to introduce the asymptotic notations. And now I think we need to turn off the lights. So the next few slides are kind of screenshots from a video that I made quite a while ago. I'm going to share. Oh, it's there. So the video is at this tiny link. And I want you guys to go through this video after the lecture, okay? At 5x speed, okay? Okay, so what we have done so far is that we have defined what an algorithm is, okay? Algorithm is a list of instructions that is independent of programming language and hardware, all right? Now our goal is to count the number of primitive operations in that algorithm, all right? And for that, we are going to use something called asymptotic notations, big O, big omega, and big theta, maybe little o and little omega as well. And that can be done using three rules. One of them is that we don't want to find the exact number of instructions, okay? This kind of counter of what I said a moment ago. We don't want to count the exact number of primitive operations or instructions. What we want to do is we want to bound that number, okay? So we want to say that if your input size is n, then your algorithm takes at most this much amount of time, or at least this much amount of time, okay? So we're not going to say that it's going to take exactly this much amount of time. Okay? We don't care about the exact number of instructions. We're going to abstract away that thing. We're going to just bound it from above or from below. All right? One important part here is that we care about how that runtime scales as a function of the size of the input. Okay? So, for example, you said that for finding the maximum in a list, your runtime complexity is big O of n. That tells you how that complexity increases as the size of the list for which you want to find the max increases. Okay? So big O of n says that it increases linearly. Okay? So that's what we care about. Also, at times it becomes a challenge to compute the size of the input. For example, it makes sense to say that the size of a list is the size of the input for the finding maximum problem, okay? But let me give you another example. What's the size of an input for a problem where you are asked to reverse a string? So what's the size of the problem if I ask you to write an algorithm to reverse a string? Okay. Right. It's the length of that string. It's the number of characters in that string. It makes sense to say that that's the size of that input. All right. So for finding maximum, your algorithm was a linear time algorithm. It takes big O of n time, right? For I'm going to use the board for, right, so finding So said it's linear amount of time, right? Stop me or disagree. Stop me at any point where you disagree with me, okay? So for a problem to reverse a string, your input is n, and your algorithm takes. Do you have an algorithm in mind when you want to reverse a string? Yeah. Okay, I'm going to try. Sorry about that. I should be more. Okay, so reverse. I hope कि मेरी spelling ठीक है. Okay, for to reverse a string, how much time do you need? N by 2. Do you? Oh, fine. Okay, cool. Okay, so linear again. Okay, that's justifiable. Okay, here's another problem, which is so this was 2. 3 is prime. Okay. I give you a number and then ask you the question that is this number a prime? Okay. How do you do it? How do you figure out whether a number is prime or not? It's not that hard. I give you a number, 13, and I ask you the question, is it prime or not? How do you do it algorithmically?
You go from 1 till half of that number.
Okay, so he's saying that loop from 1 to n over 2, try to divide that number by everything. If anything divides it, then it's not a prime, otherwise it's a prime. Make sense? Can we do slightly better? Can we do slightly better? His algorithm is that divide n by from 2 to n over 2, and you have a better algorithm? Yeah. How would you know that they are prime? Okay, so his answer is that you divide n by all the primes from 1 to n over 2. I think there's going to be a problem deciding which of those numbers are prime unless you have a huge table, right? Think of n as, I don't know, a really big number. You had something to say?
I had to say.
Okay, anyone else? No? N over 2 is the best we can do? Yes?
I think we can improve it by, if the number is not being divided by 2, we will not divide it by any of the even numbers.
Okay. Yeah, so this is pretty much the same algorithm which he said, which is that if it's not divisible by 2, then it's not going to be divisible by 4 or 6. And his idea was if it's not divisible by 3, then it's not going to be divisible by 6, 9, and so on. Okay. Can anyone do slightly better? I was assuming, yeah. Yeah. What's your name? Okay, cool. So you don't have to go to n over 2. Square root of n is all right. Okay, let me write this down and you'll probably agree with me, okay? For this one, I'm writing an algorithm here which does this. Okay, so this is my problem. Is prime. My input is n. I'm going to loop for 2 to square root of n. Okay, square root of n is enough. If you can see this, right? You can see this, right? Okay. If I divides n, then you return no. Okay. And if this loop completes, right, over here, then none of these numbers divide, and then you return a yes. All right? Do we all agree that this is the correct algorithm? if n is divisible by something, then n is definitely divisible by something between 1 and between 2 and square root of n, right? Yes, no? Okay. I don't mind if you want to write a n over 2 here, okay? But convince yourself that this is enough, okay? But let's say we have n over 2 here, okay? So what kind of algorithm is this? Is it a linear algorithm, quadratic, cubic, exponential? What else do we have? Question? Anyone? So first of all, I can, what's the runtime of this algorithm? I think based on the knowledge you have from data structures, this is a fair question to ask. Yeah? You're saying it's linear, okay. Before we say that, so I'm going to write this. I'm going to say that it's big O of n, right? We agree with that, right? I have a loop which runs to up to n over 2. So this would be square root of n over 2, which is same as, sorry, big O of n over 2, which is same as big O of O, okay? And this guy says that it's linear. Does anyone agree, disagree? Yeah. Hold on a second. Let me remove the complexity. I am crossing this and replacing it with n over 2 just to make this conversation slightly more fluent. Okay? So I am running a loop from 2 to n over 2. Yeah. And then if anything in that range divides, and I'm going to return no, then because it's not a prime then, right? And none of those numbers divide, and then it's definitely a prime, okay? And now we are just computing its runtime complexity, which is, you said linear. Does anyone agree or disagree? You got to pick one side. Yeah. What? You agree, okay? Yes, no? Agreed, okay. A node would do. Node, or a raise of hand if you agree. I'm noting the people who are not raising their hands. I'm going to assume that that means that you disagree. And if you disagree, you're going to have a reason to disagree. Okay, hands down. People who disagree. Whoa. No one disagrees? Any of the TAs disagree? No? All right. This is not a linear time algorithm. If it were a linear time algorithm, I kind of wasted your 10 minutes or so, I guess, right? It's not a linear time algorithm. What the heck is it? If it's not linear. Yeah? Oh, sorry, what? Can you speak a bit louder? A rational one. What's that? Oh, it's a polynomial one. Okay. Okay. I should have put it somewhere in the list. So she says it's a polynomial algorithm. No, it's not a polynomial time algorithm. Okay? I'm running out of time, so I'm going to give you the answer. It's this. It's an exponential time algorithm. Yes. Sorry, what? Oh, so good question. So his question is, if I replace this number with square root of n over 2. Does it change anything about what I have said so far? The answer is no, it does not. Both of these algorithms are exponential time algorithms. If anyone can give me one line reason why, that would just make my day. Think about it. I'm going to give you 30 seconds. We have 30 seconds. Okay. Go ahead. Glasses, yeah. Okay, so he's saying that we are not adding a constant somewhere. That's the reason. No, yeah. Yes. Then it's divisible by? That's true. That's true. Why does it make this algorithm exponential? So there's no question about the correctness of this algorithm. This is correct. There's nothing wrong with it. Okay? It does what it is supposed to do, which is to figure out whether it's the number I'm giving you is prime or not. Okay? The correctness is not the issue here. The issue is how long it's going to take. Is it going to take exponential amount of time or linear amount of time? These are the two options currently we have. Yeah.
The same order basic steps as an exponential algorithm.
Okay, try to rephrase what you're saying.
So like it finishes in the same time as an exponential algorithm.
It finishes in the same time as an exponential algorithm. That's a convoluted answer. I mean, it's an exponential algorithm, right? So we have to agree with that. But why? Why is this? Why I'm saying that this is an exponential algorithm? Yeah.
Could it be because square root of n is just n to the power half? So as n increases, it's like the primitive operations are increasing exponentially?
So what I'm saying is that whatever the reason is, it should be valid if I replace square root of n by n over 2. Yes? Yes? Yeah, blue shirt. Awesome. A really good answer. Not the answer I was looking for, but a really good answer. Really good point to comment here. So over here, I'm assuming कि ये वाला जो काम हुआ है ना, where I check whether a number divides n or not, is a primitive answer. So he's saying that you need to be careful about that. Okay. But for now, we are okay. In this example, we are okay. We are assuming that checking whether a number divides another number and the mod is 0 is all right. We can assume that it's going to take constant amount of time. I heard one of your reasons. I'm going to come back to you in a moment. You have something to say? Yeah. Ahmed. Yeah, that's the answer. Okay. It's exponential in what matters. And what matters is the size of the input. Remember, we compute the time complexity as a function of the size of the input as compared to as a function of the input. Okay? Let me say it one more time. We compute the runtime as a function of the size of the input and not as a function of the input. Okay? So your input here is a number n, right? What's the size of the input? What's the size of the input? What's the size? What's the size? The size is the amount of memory you need to write down the input, right? So if you have a number of, if you have a list of numbers, it's the amount of memory that's required to write down that list. Okay? What's the amount of memory you need to write down a number n? You had something to say? So, okay, a very valid question or comment. But here's the thing. Sometimes things matter. For example, when I'm trying to find maximum of a number, then it makes sense to assume that जो numbers हैं, they're going to fit in the word of the memory. That's a reasonable assumption. No one stated it. You can state it if you want to, and it's a good thing to state it. But it's usually reasonable to assume that the numbers in that list are not drastically different from each other. Okay? So it's kind of a reasonable assumption that I'm making, that when I'm asking you to to check whether a number is prime or not, then there is no other measure of the size of the input, other than figuring out how many bits you need to write down that number, right? So for finding out whether a number is prime or not, those numbers don't make any sense. For example, the numbers that are going to fit in, for example, 32 or 64-bit memory are somewhat constant to check कि वो prime है या नहीं है. Okay? So if your algorithm only takes one number, then you need to figure out what's the size of that number, how big that number is. If it's a list or if it's a string, then you figure out how many numbers are there. Okay? Okay. Cool. So the point here was that it's big O of n, which is correct, but n is not the size of the input. The size of the input is the number of bits required to represent n, which is log base 2 of n. Okay? That's your size. And whatever you want to call it, let's call it k. Your runtime is big O of n, which is big O of 2 to the power k, or 2 to the power the size of the input. Okay? That's what makes this algorithm exponential. Primality checking whether a number is prime or not was a very notorious problem for about 30, 40 years in computer science. In 80s, it was finally cracked, and polynomial time algorithm for checking whether a number is prime or not was given. And it's super hard. I think it's going to take a whole semester to describe that algorithm. Do you have a question? K is the size of the input. K is the name of the size of the input. Okay? And which is the number of bits required to write down the number. We're running out of time. You can write down your questions in Slack, and we'll get back to you. Couple of action items for you before you leave. Pick up your favorite book, whichever it is, okay, and go read 2 chapters of it. One of them is on asymptotic notations. The other one is on order statistics or selection algorithm. We're going to talk about selection algorithm, hopefully in the middle of next lecture. Yeah, that's about it. I'm going to see you on Wednesday. Thank you, guys.